Hello everyone. Welcome to the 20th lecture on general topology. In this lecture, we'll discuss about compact spaces. This is in continuation to the previous lecture, lecture number 19. In that lecture, we have introduced compact spaces. In this lecture, we'll study some result based on compact spaces. We'll discuss about subspaces, image of a compact space, and some result related to compactness and normality. Before proceeding further, let us recall the definition of a cover, a open cover, and compact space. Let X be a topological space. A collection U of subsets of X is said to be a cover of X if union of elements of this U is equal to X. That means if X is a topological space, then a collection U consisting of subsets of X, this collection U is a cover of X if union of all the members of U is equal to X. Let us consider this topological space X. Now collect some subsets of this topological space X. Here we have the first subset, second subset, third subset, like this. We have collected many subsets of this topological space X. Let this subsets of X be the collection of subsets of X. This collection U is said to be a cover of X if union of all these members of U is equal to X. That means union of all these subsets covers the entire space X. If all these members, all these subsets is an open subset of X, then that cover is known as an open cover of X. So if all members of the collection U are open subsets of X, then U is said to be an open cover of X. What is a compact space? A space X is said to be compact if every open covering U of X, there exists a finite subcollection of U which covers X. We know that closed interval 0, 1 is compact, but open interval 0, 1 is not compact. So every subspace of a compact space need not be compact. However, closed subspace of a compact space is compact. Let us prove this. Every closed subspace of a compact space is compact. Let X be a topological space and Y be a closed subspace of X. We have to prove that Y is compact. To prove Y is compact, let us take an arbitrary open cover of Y by sets open in X. Let U be an covering of Y by sets open in X. Since Y is closed in X, complement of Y is open in X. So we have taken this collection U as a cover of Y by sets open in X. That means the members of this collection U are subsets of X and those subsets are open sets in X. Now we have that Y is a closed subset of X. So complement of Y is open in X. Now the collection U along with the open set X minus Y, complement of Y, is an open covering of X. Because this U covers X, covers Y, along with we have taken complement of Y. This new collection V is equal to U union X minus Y, that means complement of Y, is an open covering of X by sets open in X. Since X is compact, this open covering has a finite subcovering. Since X is compact, V is an open covering of X. So there exists a finite subcollection of V. Let us denote it as V dash, which covers X. If the subcollection contains the set X minus Y, complement of Y, if this subcollection V dash contains this set X minus Y, then discard this set. from V dash. The remaining elements of V dash is a finite subcollection of U which covers X. If the subcollection V dash doesn't contain the set X minus Y, then V dash itself is a finite subcollection of U which covers Y. Because in V dash, this V dash is a finite subcollection of this V. And what is this V? This V is U along with X minus Y. That means the subcollection of V, we got V dash. If this V dash contains X minus Y, then discard this X minus Y, then we have that finite number of open sets in V dash which covers Y. And if this V dash doesn't contain X minus Y, then V dash itself is a finite subcollection of U which covers Y. Hence Y is compact. So here we have proved that closed subspace of a compact space is compact. Now here we have another result. Image of a compact space under a continuous map is compact. Let X be a compact topological space and F be a continuous map from X to Y. We have to prove that image of X under F is compact. That means we have to prove F of X is compact. Now to prove F of X is compact, let us take an open covering of F of X. Let U be an open covering of Fx. Since F is continuous and we know that inverse image of a open set is open in under a continuous mapping. Since the members of this U are open sets, F inverse of members of U are open in X. So since F is continuous, the collection F inverse U, whereas this U belongs to our collection, is an open covering of X. Because F is a mapping, continuous mapping from X to Y. Here we have taken an open cover of Y. Since we have taken an open cover of Y, inverse image of every element of that open cover is an open set in X because F is continuous. So we have this collection F inverse U where U belongs to the collection U is an open covering of X. Now we have that X is compact. As X is compact, this covering F inverse U has a finite subcollection which covers X. Let the finite subcollection be F inverse U1, F inverse U2, F inverse U3, F inverse UN. These are finite number of elements from this collections. Since F inverse U1, F inverse U2, F inverse UN covers X, image of elements of this collection covers F of X. And image of all these F inverse U1, F inverse U2, F inverse UN is nothing but U1, U2, U3, UN. And here this U1, U2, U3, U4 up to UN is a finite subcollection of the collection U, which covers F of X. So F of X is compact. Now here we have one more result. Every compact subspace of a Hausdorff space is closed. Let X be a Hausdorff space and Y be a compact subspace of X. We have to prove that Y is closed. To prove Y is closed, we have to prove Y contains all its limit points. As we know that a set is closed if it contains all its limit points. So to prove Y is closed, we have to prove that Y contains all its limit points. Let X be a point outside Y. Now we have to prove that this X is not a limit point of Y. Since X is not in Y, X is in the complement of Y. Now if we take a point in Y, then that point and this point X are two distinct points in the space X. Since the space is a Hausdorff space, we know that in a Hausdorff space, for every pair of distinct points, there exist two disjoint open sets which separates them. So by Hausdorffness of X, for every Y in Y, there exist two disjoint open sets Uy and Vy, such that X belongs to Uy, Y belongs to Vy, and Uy intersection Vy is empty. This is because X is Hausdorff and this Y belongs to Y and X belongs to complement of Y are two distinct points. X and Y are two distinct points. For these two distinct points, we have two disjoint open sets Uy containing X and Vy containing Y, and intersection of Uy and Vy is empty. Here we have this topological space and here we have Y. We have taken a point outside that. We have to show that this X is not a limit point of Y. So for every point in Y, by Hausdorffness, we have two disjoint open sets. The open set which is containing X, we have denoted as Uy, and the open set which is containing Y in Y, we have denoted this open set as Vy. So for every pair of distinct points, we have two disjoint open sets which separates them. If we vary this Y all over the space, Y or all over the set Y, then Y and X are two distinct points. If our Y is here now, then this Y and this X, which is lying outside Y, are two distinct points of X. So by Hausdorffness, we'll get two more open sets, two disjoint open sets, which separates X and this Y. So if we vary this Y all over Y, then we'll get Vy's containing that Y. Let us collect all such open sets. By varying Y all over Y, let us collect all such open sets Vy's. Now the collection Vy, whereas Y is varying over Y, is an open cover of Y by sets open in X, because each of these open sets which is containing the point Y is a open set in X. Since we are varying this Y all over Y, these open sets, union of open sets, will cover the entire subset Y. So this covering U is an open covering of Y by sets open in X. Since Y is compact, we have taken that Y as a compact subset. So Y is compact. So U has a finite subcollection Vy1, Vy2 up to Vyn, which covers Y. Here we have the open covering U and which covers Y, and Y is compact. So we have finite number of elements here as Vy1, Vy2, Vy3 up to Vyn, which covers Y. Now for each I, let us collect all corresponding open sets Uy1, Uy2 up to Uyn containing X. That means for this Vy1, if suppose the first point Y, for the first point Y, we have Vy1. Then correspondingly, we have a Uy1 here which contains X. Collect that Uy1. Similarly, the second open set, suppose Vy2 contains this Y. Then correspondingly, we have this Uy2 which contains X. So for each I, let us collect all corresponding open sets Uy1, Uy2 up to Uyn containing X. So here we have n number of open sets uy1, uy2, uy3 up to uyn, which contains the point x, and n number of open sets vy1, vy2, vy3 up to vyn, which covers y. If we take union of all these by's, that will contain y. And if we take intersection of all these n number of open sets uy's, that will contain x. Now let u is equal to intersection of I is equal to 1 to n uyI, and v is equal to union of I is equal to 1 to n vyi. Clearly, this u is intersection of uyi's from I is equal to 1 to n, and each of these uyi contains x. So this u contains x, and union of I is equal to 1 to n vyi contains y, because this collection vyi covers y. So union of this vyi is equal to v contains y. So we have u and v are two disjoint open sets containing x and y respectively. Thus u is an open set containing x which doesn't intersect v, because u and v are disjoint. So u contains x, u is an open set which contains x but doesn't intersect v. Whereas this v contains y. So u is an open set containing x which doesn't intersect y, because y is a subset of v and u doesn't intersect v, so u doesn't intersect y. So here we have an open set u containing the point x which doesn't intersect y. So this point x cannot be a limit point of y, because we have an open set containing this point x which doesn't intersect y. So x is not a limit point of y. Since we have taken x as a point which is outside of y, and here we have seen that x is not a limit point of y, we can say that there doesn't exist any limit point of y outside y. So y contains all its limit points. Since y contains all its limit points, here we can say that y is closed. This completes the proof of this theorem. Now next theorem is every compact Hausdorff space is normal. Let us prove this. Let X be a compact Hausdorff space. We have to prove that X is normal. To prove X is normal, let us first prove X is regular. To prove X is regular, let us take a closed set A and a point outside it. Let A be a closed set in X and X be a point outside it. Let us see whether we have two disjoint open sets which separates A from X or not. Now for every Y in A, we have two distinct points here, X and Y in X, because Y is in A and X is not in A. Therefore this X and this Y are two distinct points in X. And we have that X is a compact Hausdorff space. So let us use the Hausdorffness condition. Here we have the topological space X. Here we have A, which is a closed subset of X. And here we have a point X which is outside A. We have taken Y as a point in A. So X and Y are two distinct points here. So by Hausdorffness, there exist two disjoint open sets, whereas one of those open set contains X and the other one contains Y. So by Hausdorffness of X, there exist two disjoint open sets Uy and Vy, such that X belongs to Uy, Y belongs to Vy. Here this is our Uy which contains X, and here we have Vy which contains Y. Now let us vary this Y all over A. So varying this Y all over A, we will get a collection of open sets By. And this collection U containing By for every Y belongs to A is an open covering of A. So for each Y, we will get a By corresponding to this X. Corresponding to this X, we will get a Uy which contains X, and corresponding to every Y in A, we will get a By which contains Y. Now if we collect all these Bys containing all points Y in A, we will get a cover of A. Since A is a closed subset of the compact space X is a compact space, and A is a closed subset of X. And we know that closed subset of a compact space is compact. So A is compact. Now here we have U is an open covering of A, and A is compact. So this open covering has a finite subcollection U dash of U which covers A, where our U dash is By1, By2 up to Byn. This U dash is a subcollection of U which is finite. Since this is finite, we have denoted as By1, By2, By3, Byn. These are only notations. 1, 2, 3, 4 up to n are notations. These Bys we have taken from this U because this U contains all Bys for each Y. Now we have just finite number of Bys, and we have denoted it as By1, By2, By3 up to Byn. Now let us take the intersection of all Uyis from I is equal to 1 to n. Since each of these Uyi contains X, if we take the intersection, then that intersection will also contain this point X. Let U is equal to intersection of I is equal to 1 to n Uyi, then U contains X. And here we have finite number of open sets By1, By2, By3, Byn. Since those finite number of open sets covers A, take their union. Then their union contains the subset A. Let us denote B is equal to union of I is equal to 1 to n Byi. Here we have U and B, two disjoint open sets containing X and A respectively. U contains X and A is a subset of B. U and B are disjoint. So the space is regular because we have taken a closed set A and a point outside it X, and we got that there exists an open set U which contains the point X, and there exists an open set B which contains the closed set A, and both the open sets U and B are disjoint. So the space is regular. Now we have to prove that the space X is normal. To prove X is normal, let us take two disjoint closed sets in X. Let A and B be two disjoint closed sets in X. Now for each point A in A, here we have the topological space X and we have two disjoint closed sets A and B. Now for each point A in A, here we have a point A and here we have a closed set B. We know that the space is regular because just we have proved that the space is regular. So by regularity, there exist two disjoint open sets. One of them contains the point A and the other open set contains the closed set B. If we vary this A all over A, then we will get open sets which covers A. Now let us, by regularity of X, there exist two open sets OA and WA, such that OA contains A and WA contains B, whereas OA intersection WA is empty. Now this collection OA, because we are varying this point A all over this set A, then this collection OA for A belongs to A is an open covering of A. Now A is a closed subset of X. So it is compact because we know that closed subspace of a compact space is compact. Since X is compact and A is closed subset of X, A is compact. And this B is a collection of open sets which covers A. Since it is compact, it has a finite subcollection. So there exists a finite subcollection V dash. Let us denote it as OA1, OA2 up to OAn. These are n number of open set we have taken from here, OA, the collection B. So this B dash is a subcollection of B containing finite members which covers A. Now collect all such corresponding open set WAI. Here these OA1, OA2, OAn are open set containing points A in A. So for OA1, suppose this is the open set OA1 which contains A. Then the corresponding open set which contains B is this. Let us collect this corresponding WAI which contains B. Similarly, if our A is somewhere here, then we will have an open set like this, which is our OA2, and correspondingly we will have another open set here, WA2, which contains B. Collect that WA2. So now collecting all open set WAIs containing B for each OAI, we have this. Take the intersection of all those WAIs. Since each of these WAI contains B, their intersection will also contain B. And this intersection of WAI is equal to W. So W is an open set which contains the closed set B. And take the union of all OAIs. And here OAI is a finite subcollection which covers A. So if we take the union of all these OAIs, that will contain A. And this union let us denote as O. O is an open set containing this set A. So now we have two disjoint open sets. This O and W are two disjoint open sets containing A and B respectively. Clearly, O and W are two disjoint open sets in X containing A and B respectively. Hence, X is normal. So every compact Hausdorff space is normal. This is all about in this lecture. In the next lecture, we'll study about some variants of compactness like limit point compact and locally compact.